Okay, so thank you very much, Dan. Okay.
Can you please say that we have started the first presentation?
Is the point, yeah. So this talk is, as Dan said, this talk is going to be about so playing with data assimilation using machine learning tools, or trying to combine them both. But my point will be that I'm essentially doing machine learning with new tools. But I'm essentially doing data assimilation, but with new tools, machine learning tools. And the game here will be to do traditional traditional data assimilation, but incorporating the model as one of the control variable of the problem. So this will be the main emphasis on this talk. And so maybe I'll try to answer some of Takemasa's questions that he had at the end of his talk. Yeah, I mean, about the connection between data assimilation and machine learning, at least on the specific topic of reconstructing the dynamics of models. Okay, so my standpoint is really from a data assimilation perspective, and I'm going to introduce the problem from this perspective. Okay, and so as we know in data assimilation, and that is used actually for doing numerical forecast in geophysical models, the performance of the scheme and the accuracy of the scheme, the usefulness of the scheme actually crucially depends on both the initial error condition, okay, and this is why data assimilation was applied sequentially on chaotic dynamics, and on model error. Okay, so initial condition is an intrinsic problem to the chaotic flows, and model error comes from the way we model the physics. Okay, and there are methods, so I'm not going to speak about initial condition. This is the purpose of classical data assimilation. I'm going to focus on model error. And there are a lot of ways in data assimilation that have been introduced in geophysics to modeling to try to mitigate the impact of model error. So they've been like additive noise, so weak parametrization, incorporated into the data assimilation scheme. There's been the modeling of under reconstruction of uncertain parameters of the physical models. There have been schemes that are supposed to mitigate the impact of model error, like physical-driven stochastic perturbations, subgrid schemes, inflations, and other types of schemes. Now, more recently, there have been attempts to try to forget about the model, not really replace the model, but instead try, look for the resolvent of the model, or try actually to, using only data, try to infer a way to move from time tk to time tk plus 1, where we get the next batch of observations. And this is the kind of attempts that were not at least permitted in data assimilation so far, but because of those bold attempts, at least on some low order or intermediate order model, this is now a question that we can raise and try to address. And so there have been, as Ronan mentioned yesterday, there have been, for instance, attempts to use data assimilation using analogs. There are many other attempts, like diffusion maps, for instance, to only use data, try to infer some kind of a resolvent for the model, not using any model. Or the use of neural networks, so eco-state networks and other deep learning techniques, to try to, again, replace the model with some kind of a resolvent. Okay, a slightly different game is that consists actually in trying to really formally replace the model, not only reconstruct the resolvent, but really infer equations for the model, some kind of equations for the model, and reconstruct whatever model we could have in data assimilation. So examples, typical example, recent example of trying to achieve this is using a set of, so this is now looking at resolvent, but trying to have an explicit expression for the resolvent. So introducing a huge set of regressors on which you would expand the resolvent and look for the coefficients of those regressors. This is typically the approach of Brenton and his team. You can also design, as Ronan mentioned yesterday, you can design neural network that mimic integration schemes to make it closer like a model, looks closer to a model. And so that actually looks really like, it could look like explicit equations for the model, for any surrogate model that you try to infer. Okay, so in this talk, I'm going to try to use a data assimilation framework to infer not only the state trajectory in the model and possibly some parameters, as we do usually in data assimilation, but also infer a surrogate model for the dynamics, so using only observations, but those observations, thanks to this data assimilation framework, I'll be able to use partially and noisily observed measurements on the physical system. Okay, so I'm going to introduce first a couple of representations for the surrogate model, so the mathematical way to represent the model that I'd like to infer using the observations. The first one, which turns out to be extremely simple but also extremely efficient, is just to have an ODE representation of the, at least for low order model, is to have ODE representations of the model, of the surrogate model. And so it looks like just these first order equations, these first order ODEs, with phi being the flow rate, and it's just written as the product of the matrix A of coefficients, so the weight, that multiplies a set of regressors, okay? But now I'm not looking for the resolvent of the model, okay? So I don't need necessarily a lot of regressors. I'm really looking at the equations of some kind of ODE representation that I could possibly integrate on time. So I don't actually have to use a lot of regressors, and I will only consider constant linear terms and bilinear terms here, okay? Because we know that some of the models that some lower chaotic models actually can decompose into this kind of simple monomials. And of course, as you will integrate them, you will be able to generate higher order terms easily. I mean, if you build a resolvent from this kind of representation, you will be able to have higher order terms. But of course, if you don't have any symmetries in the system, then the number of regressors, even those simple ones, will scale like the square of the size of the system. So that's an issue, and we have to use symmetries and assumptions to make that simpler. Okay, and the main one is certainly locality. So that's an assumption that is not too drastic for geophysical models. So it only means that the PDEs depends on local operators. Okay, or if you consider discretized systems, ODEs, it means that the monomials that you will have as regressors, okay, will have variables that depends on a stencil. So a local set of variables around a given node, so that you actually consider a limited set of relevant set of regressors. So local doesn't mean that you do perform data assimilation on a local domain. You still could have long-range correlations. It only means that the physics can be described in terms of local operators. So if you do so, and you have a stencil typically of size L or 2L, then the size of the A becomes sparse, and the effective size of A is actually the size of the system, linear in the size of the system, okay? That multiplies something that depends on the stencil size. Okay, so this is now numerically tractable even for a high-dimensional system. And another assumption that we can actually make, which is not as realistic, but it's easy to make tests, is just transactional invariance, so homogeneity for the statistics. And then in this case, A is just a set of coefficients, just a small vector that depends only on the stencil size. Okay. Now that we have this representation, okay, we can actually use this representation and integrate it to build a resolvent from time tk to time tk plus 1, where we have the observations and we need to integrate them, and so we can compose a set of integration, so NC integration schemes, and each integration schemes is any numerical integration schemes that you would like to use, possibly explicit to make it simpler to use. And here, this is typically a Runge-Kutta method that we can use. And of course, in this Runge-Kutta, we do use the kinetic flow representation that I introduced on the previous slides. Okay, so this is here to build a resolvent from this thin representation. Now, once you can generalize that and use a neural network and actually a residual neural network to make it simple. And in this case, so considering the thin algebraic representation that I've just shown with a simple set of regressors, you can actually that was built without any machine learning libraries. Okay, without TensorFlow, PyTorch, but you can actually do so if you want to. if you want to rely on those libraries, and you can also implement them as a neural network. But you can also, if you really want to heavily rely on those libraries because they are well-tuned and run easily, then you can actually generalize this kind of representation and use convolutional layers. So if you want to use the two assumptions of local and homogeneous, you're going to use convolutional layers. But if you want to only use the local assumption without the homogeneous assumptions, so without transactional invariance within the system, then you can use locally connected convolutional layers. And so the schemes is exactly the same as before, except that now we have replaced the elementary, the kinetic flow rate by just a neural network. So that's a typical simple example here. Okay, but the rest is the integration from time tk to time tk plus 1 using composition and a numerical scheme. Okay, now now this is the tools that we have, and those are only tools or representation. Now I want to have a Bayesian standpoint on the data assimilation standpoint on the problem of reconstructing the state trajectory, but also the model. Okay, and so the Bayesian standpoint on this is would be this one, and so that's a hierarchical formula where we use Bayes' rule and so on. But we're looking for the model, and here it's important to consider that we are only looking at the not static dynamics, but the set of coefficients of the flow rate does not depend on time. Okay, they are the model error statistics and the state trajectory over the window on which we actually learn the dynamics and the state. And I've put in the known statistics, I put the model error. We could actually put that into the parameter that we would like to estimate, but this is actually not as important for the following example. And it's not, I mean, Q is much more difficult to estimate actually than R. And if I put R into it, we know that there are additional issues that we know in data assimilation when we do so. Anyway, so we have using a hierarchical hierarchical Bayesian formulas, we can actually write it in terms of a likelihood of the observations given all the other parameters and the state. Okay, that multiplies the prior on the state given that we know the model and the statistics. Okay, and if we write it in terms of the cost function, we end up writing a weak constraint for the var. Okay, but because you're also interested in the statistics, we need to write explicitly the statistics of the errors in this weak constraints for the var. Okay, and this is so here now the dynamics, I mean, is really the weights of the A matrix is really a control variable of the problem. Okay, and because we have formulated that from the Bayesian standpoint and this data assimilation standpoint, I mean, it comes easily that we can actually handle partial and noisy observations in the system. Okay, and if we want to connect that to classical machine learning, so elementary machine learning, we can actually observe the whole system, take the observation matrix to be the identity, and let the noise goes to 0. So the observation errors goes to 0. And in that case, the limit, the cost function which is the limit of this one turns out to be just this simple least square, which is the basic classical machine learning cost function that people would write. Okay, so this is really the rigorous limit of this cost function. Okay, so this is really the connection between, this is an easy connection, an obvious connection between machine learning and data assimilation, and where data assimilation actually embeds this kind of machine learning regressors. Okay, so now I'm going to describe what we have done and what we are currently doing. So what we have done initially is looking for a solution of this cost function, but not looking at the model noise, because that's quite intricate. Because of course we would like to estimate Q, but it also depends. It parameters also A. So optimizing on A and Q has to be. I mean, it's a tricky part that we'll come into later. So as a first step, we did not look into Q. We considered it to be known and fixed. And we look only for the dynamics and the state parameter and the state throughout the window. Okay, and there are many ways to add. So this is an optimization problem. Okay, this is a weak constraint optimization problem, and there are many ways to solve it. And the first thing that we tried was actually using this thin algebraic representation. We used the full variational approach. So looking like this is really 4D var. So solving for both, I mean, altogether the coefficient in A and the state trajectory X. Okay, and this is one of the first attempts, and it works, but this is one way, not necessarily the most efficient way, because A actually does not depend on time. So whereas the trajectory depends on time. And this is without actually using machine learning libraries. Okay. So the second option is to use coordinated descent, meaning that you will first solve for A, and then X, the trajectory, then A, X, and iterate over them. Okay. And the one way to do it is to use, again, variational setup using we constrain 4D var for X, and then optimize using variational approach, relying or not on machine learning libraries. Look for the optimal A, and then go again to X, and then A. Another option that really takes into account the fact that A does not depend on time, whereas X is a full trajectory, is to use in the step where you optimize on X, instead of using 4D var, you will use an ENKF or a Kalman smoother, and a Simon Kalman smoother. Okay, so this is another thing that we did, and the scheme for this particular technique is to so first fix the model, then use the ENKF or ENKS, and then once you've got an estimation for the state trajectory, then you can fix it and then estimate for the model, okay, using all these reconstruction trajectory as data for the machine learning technique. Okay, and then you iterate ultimate convergence. But I'd like to point out that this is really coordinated descent, okay, no more than just a simple coordinated descent. And this coordinated descent was actually interpreted as an expectation maximization by Nguyen et al. in Renan's team. But actually, it's not really the full EM. This is really a coordinated descent, actually. It ends up being the coordinated descent. Okay, now so this was for what we did so far. And now the thing that you can actually do better, and this is really the ultimate question, if you look into the reconstructing the dynamics or try to guess what the dynamics is, you don't necessarily want to do the joint optimization of the state trajectory and the model. You really want to focus on the model and the unmodeled error that is attached to it. And then this is just the marginal PDF of the PDF that I considered so far. So I'd like to emphasize the fact that here we're not looking at the model only. We're really looking at a joint set of the model and some stochastic parameterization for the model. Okay, a simple, very simple one, not as sophisticated as what Etienne showed yesterday, for instance. But this is still a stochastic parameterization on top of this A model. So we are looking for really this set. Okay, and now we want to use almost the full power of EM. Now we use we have this the expectation step of EM using data assimilation, using a Kalman smoother over the period. It could be long or not long, depending on what you want to achieve. And then you use looking at the parameters here. We look for the coordinate. We do a coordinated descent, so optimizing on A first, and then using the maximization step of the EM to try to infer the matrix Q. Okay. So this is the algorithm that we're going to use. So this is a mix of EM. The framework is really EM, and we use almost the full power of EM, and then there is part of it is still a coordinated descent. Okay, so I'm going to show you a few numerical experiments that we've done with those methods. And they all rely on generating a set of observations, okay, with some hidden model. That could be or not, that could be identified or not with the data assimilation machine learning technique that you use. Okay, maybe it's not in the space of all the models that you could reconstruct, so there is a difference to make there. And then we use those observations, okay, to train the data assimilation machine learning setup. Okay, and then once we have an estimation of the model, we can actually make some forecasts to test the validity of this model and compare it with the truth, like in any twin experiment. Okay, except that we're looking for the trajectory, but also but mainly the model here. And the metrics that we can use is first, if the model can be identified, that is, if the model is actually could be represented as a simple ODEs. so that actually you could actually find the exact model if you would like to. Then you can compare the set of coefficients that you found with the true ones. Okay, but this is only valid if the model can be identified. But otherwise, you would have to use root mean square error, okay, between the reference model and the surrogate dynamics. So making forecast, a lot of forecast and sample forecast, and trying to compute scores for those forecasts, comparing with the reference. And also for climatological properties of the model. So of course, this is for short-term forecast, and this is for long-term properties of the model. You look for instance, Lyapunov spectrum and power spectrum density. Okay, so a typical example, when you observe the full system and you use noiseless observation, so more like a machine learning type of problem, then you can, so using the method, actually, you can reconstruct the Lorentz-Stick-free model perfectly, okay, almost to machine precision. And the same is actually true for the Lorentz 96 model, okay, using locality assumption. And here, this is homogeneity assumption too, but you don't need it. I mean, the result would be the same using heterogeneous assumptions on the Lorentz 96 model. Okay, and this is the typical kind of graph that you can plot where you compare a trajectory. So this is over time, and this is the site of the model. So there are 40 variables in the Lorentz 96 model. And this is the reference trajectory, and this is the surrogate model trajectory, and this is the difference between the two. And you see that you can actually, so this is really a full, this is almost fully identifiable model because we use different, in this game, in this example, we use a game where we actually integrate the true reference model differently from the representations that we have. We use a different scheme. So that actually, mathematically speaking, we are close to be able to identify the model, but not really fully. So, but still in this case, we can have very extreme short-term prediction using the surrogate model, up to 6 Lyapunov times. Okay, and we can play the same game with Kuomato-Sebastinsky. That's actually look even better. And now in this case, the model is not really, cannot really be identified because this is a PDE and not an ODE, and we have an ODE representation. But if you do some Taylor expansions to check what would be the PDE coefficient, if using this surrogate model, it turns out that actually it's quite close to the Kuomato-Sebastinsky equation. Okay, and we do have the proper set of coefficients for the free terms, and we have some noise in the higher order terms of the PDEs. But the reconstruction for short-term property is very good. Now this is using the full EM cycle where we do estimate the error. So we estimate the model, but also the stochastic scheme that is attached to it. And you would have typically this kind of, so using 10 iterations for the EM. And this is on my video card game, so that's kind of because of course we don't have that at work. I mean, we have to buy our own video card. So this is very an old one, it's like 2 years old one. And it runs very fast in a few seconds or a few minutes if you want to really want to have a long window. So you can infer the model, and this is the typical forecast skill that you will have. Okay, this is normalized root mean square error, normalized by the typical dispersion of the model, climatological one. So it's useful. So the forecast is useful up to 1, and which is pretty far. And this is the Lyapunov spectrum, which is very close to the true one. And this is the same for the power spectral density. Now, the game is more interesting with 2 scale because we don't have this is with noisy observations, okay? And this is full observations of the system, but actually you can do so with only observing half of the system. But now this is really a large noise that we consider, the typical noise that we would consider for data simulation experiment. So it's not really granted to find the dynamics. You need really to tune the method. Now this is the 2-scale Lorentz model that Colin Goodson introduced yesterday. And this is the full system with the slow modes here, which looks like the Lorentz 96 model. Okay, and this is the fast modes. Okay, and so we are looking for a model that has the same number of variables as the coarse mode. So we're looking for the coarse mode dynamics and try to represent the impact of the fast mode and the genetic modes in the system. And this is the typical reconstruction that we have. and with these typical statistics that we found. And for the forecast skill, and we've got something which is quite similar to the Lorraine 96, we do have longer term, actually, good forecast skill, which can be understood, but I really don't have time to explain that. But you can go up to, again, 6 Lyapunov times, actually, where the model still does good. And then this is the comparison with Lyapunov spectrum. You do have something that looks like it, but because of all this energetic mode that we do not represent, I mean, there is surely a difference between the two Lyapunov spectra. And now this is the last thing is this power spectral density. And where you do see this is the true model, okay, the full Lorentz two-scale model, where you do see the impact of the fast scale here. Yeah.
Okay, it's the power spectral is completed for what? For like one variable?
For one variable average over all the variables, yes. Yeah. And so this is the impact of the fast modes, okay? This is looking only on the coarse modes, but using for the full model here, the two-scale in blue, and you see the impact of on the fast modes here. And this is the reconstruction that you have with the surrogate model, but using not only the surrogate model, but also the stochastic noise that is actually retrieved in the data assimilation scheme. And this is really what it predicts. If you don't use this stochastic noise, you would have something actually quite different, not as good, and with a tail that would not be as good. Okay, and so typically the main message is that we can have a Bayesian data assimilation views on this kind of problem, where you can really combine data assimilation schemes and machine learning tools. I'd say the more I think about it, the more I'd say that this is really data assimilation, where we do use the powerful softwares from machine learnings. I mean, looking really into this specific problem, okay, not other machine learning problems. So you do rely on the softwares, but you still can have a Bayesian view on that. It's that you incorporate the model into the control variable. Okay. Now you need to make assumptions, like in geophysics, in general data assimilation, like locality, homogeneity. You can use this full EM technique to estimate those stochastic parameterization on top of it. And then you can using the scheme that I've introduced, you can actually use long training windows, and it's so far successful on low-order system, one-dimensional ones. And there are many other questions. Some of them we have answered over the past months, but many other remains, like non-autonomous dynamics and the use of implicit integration scheme, so because the Rungakuta was explicit. The use of online machine learning. So this is certainly easy to do, to try, but not necessarily easy to have a very good one. And the use of more complex test cases and models and higher dimensional models. And thank you.
Thank you very much.
Valerio.
So you can do your daily morning exercise, only for that, not for you, Marc. Now the question is on the last example you showed us on the two-level Lorentz 96. So if I understand correctly, you are trying, the output of your, the output is an effective model for the course, only for the slow variables, correct?
Yeah.
So this model is deterministic, or it has also stochastic components? Solid.
So it has as I mentioned, we look for this A matrix, so this surrogate representation, but also there is the model noise. So we have additive noise, Gaussian noise, that we add on top of it, and we retrieve both of them all together.
So you limit your noise, stochastic noise model to an additive one. That's that's a limitation.
No, there is the deterministic model plus the stochastic noise. This is the trace of it here.
I cannot see the top right figure. What is higher, the original one?
So higher is the original one.
Oh yeah, that's
it's more identity.
Yeah, that's what I would expect. Thank you.
I'm coming.
So uncertainty, did you look into that? Uncertainty quantification?
So we've got many control variables. So I didn't look into the, yes, because the scheme is, so it's using an ENKS, and we're also retrieving this Q matrix. So we do have a description of most of the uncertain parameters. And this is the uncertainty is really, I mean, this tail here, I mean, this is really the uncertainty quantification of of the errors that you make on the reconstruction of A. If you don't do account for Q, you would have a much steeper curve like this, below the blue one. So that's nice.
One more question for
Yes, so you mentioned that you have some observation noise. What is the amplitude of your observation noise in this case?
Here it's typically 1. It's the 1/10 of the, no, it's more. It's 3 times, no, it's 0.3 times the natural variability of the model. So it's significantly the kind of thing we consider in Lawrence 96 in data assimilation.
Thank you very much.